Okay, so hey everyone, my name is Mark, and I'm a contributor to the Optimism Collective. So I'm here today to talk about interoperability, right? So this is modular interoperability in the OP stack, right? I just want to give a shout out first to all of the incredibly talented people that helped with this. This is our little Sunny army. I don't know if you've seen the Sunnies yet, but you know, they've been starting to pick up on Twitter. They're pretty fun. Okay, so what is interoperability, right? So blockchain interoperability, it allows for chains to read the state of other chains, right? This is kind of like read-only interoperability. Technically, it's possible to have like a write style of interoperability, but that's much more complex. This talk is completely focused on just like reading the state of other chains. Okay, so design philosophy of how to build an interoperability stack, right? It needs to be minimal and flexible, right? And it needs to just work with existing tooling. Because if you're, building a complex thing that doesn't work with the existing tooling, it's gonna be really difficult to get devs to adopt it, right? And this architecture is, generic. It should be able to work with different rollup frameworks, but we have been developing this specifically for the OP stack. But, other people can also adopt it if they want. Okay, so let's start with the user experience, right? What is because you should always design features from the point of view from a user, right? If you're designing a feature without thinking about the user experience first, you'll probably have a bad time, your users might not like it, right? So, very simple, right? There's two transactions, right? You send a transaction to say OP mainnet, it emits a log. Then you submit a transaction to base, and this transaction that you submit to base, it includes a pointer to the log that was emitted on OP mainnet, and the log's data, and an address to call that pushes that log to this address, right? So, some vocabulary, right? We have an initiating message and an executing message, right? The initiating message, right? This is the transaction on the source chain, like in the previous example that was OP mainnet, right? So that's the initiating message, and then the executing message, that's the transaction on the destination chain, right? Because a cross-chain message is you have to send a transaction to the first chain and then send a transaction to the second chain to finalize it, right? And then we have this idea of a dependency set, which this is the set of interoperable chains that can all send cross-chain messages to each other, right? So, some key properties of this design, right? There's no forced inclusion of cross-chain messages. So, anytime that you have forced inclusion of some sort of cross-chain message, it adds a lot of complexity, right? If your cross-chain message can trigger execution, now you need to be aware of the gas market on the remote chain. You also need to be aware of the possibility of all possible chains sending, cross-chain messages to the same chain at the same time. You don't want to allow for denial of services, right? So if you have forced inclusion of any sort of cross-chain message, the best way to design that is to use a queue, right? Even depositing to be a validator in ETH2, right? There's a queue for that, right? Because that is a forced inclusion transaction, right? So we decided to simplify things because we want to be more scalable. If you have a queue, then now you have this kind of synchrony assumption where you have to kind of sync all of the chains. It becomes much more complicated. So no forced inclusion of cross-chain messages. Much simpler, easier to reason about. We're also leveraging out-of-consensus policy to scale. So what does this mean? So because there's no forced inclusion of these messages, it's really block builder policy. It's one of my favorite things about this design. I'll get more to it, but basically block builders will help us to scale this. So we have optimistic inclusion with fork choice enforcement. So what does that mean? Right, so these blocks that contain cross-chain messages, they are included optimistically, and the fork choice will basically reorg out blocks that are invalid. In this case, the definition of an invalid block that contains cross-chain messages, it means that it has an executing message that doesn't have an initiating message, right? So just to clarify what that means, right? Every single cross-chain message or cross-chain transaction, right? You need like two sides of it. You need the initiating side, you need the executing side. So if a block contains any executing messages that don't have a valid initiating message, that's considered to be an invalid block, gets reorged, right? So our fork choice enforces this. The fault proof also enforces this. It's kind of just like different views into the same problem. And basically, we utilize static analysis of these cross-chain transactions to let the block builders really scale to be able to like know, if an executing message has a valid initiating message, right? And I keep saying this, it's probably pretty abstract. I just said all this stuff, right? This is talking about the fork choice rule. So now getting to it, right? This is pretty much as simple as it gets, right? This is the smart contract that allows for the entire scheme to basically work, right? So static analysis, right? Require message sender equals TX origin, right? So basically, right? You want to send a cross-chain message, right? What you do is you basically take a log on a remote chain, right? Let's say that there's an oracle on a remote chain and you want this oracle's data in your local chain, right? Because that oracle on the remote chain is emitting events, right? So we want to have one oracle and then that oracle data can be used everywhere. So that oracle is emitting events, right? So what you do is you take the event that is emitted, right? Like, like in Solidity, it's like the, emit, syntax that like emits an event, right? So what you do is you have an identifier. This identifier right here uniquely identifies a single event, right? Solidity calls it an event, but like Geth calls it a log, so we got log index here. But basically we have this identifier. This identifier uniquely points to a single event across any chain, right? So we have basically like a chain ID, a block number, and a log index that helps to uniquely point to a single event, right? And then what we do is we basically see there's this message that's passed in, right? This message is the serialized event, right? Where an event can have like topics and then it can have data, right? So basically, this identifier right here points to an event, right? And this pre-deploy, it's built into every chain, right? A user sends a transaction to this pre-deploy, and basically the user is saying, I claim that this event on this remote chain exists, and I want to consume it, right? So the block builder, or like the sequencer, does like a quick check before including this transaction into their block, right? Because if the sequencer includes an event that doesn't match its identifier, then that's an invalid block and it'll get reorged out, right? And that the sequencer will lose some transaction fees, it'll be bad, So basically, right, this scheme lets you read in events from any chain, right? As long as the chain is in your dependency set, right? And the chain governor can decide that, right? So this is like the bare basic primitive that allows for a chain to read in an event from any other chain. Anyone have any questions at this point? Okay, what's up?
So as of now, are those chains will only be able to do the cross-chain interoperability if they are using an OP stack?
Right now, yes, because this is all basically secured by the fault proof, right? The fault proof will be able to like enforce these rules. And it's very, very complicated to try to build a fault proof that like works across like, say, both Arbitrum and, OP stack at the same time. Like that would just be like kind of crazy. So, this scheme right here, technically any blockchain framework can adopt this scheme. So, but we're building into OP stack. But if the question is, can an OP stack chain, use this particular scheme and interop with like, say, like a Arbitrum Orbit chain in like a trustless way, that will not be possible. Just because, it would not be able to be secured by the fault proof. But I do think that this is like a very minimal scheme that any chain could kind of adopt, if that makes sense.
And the OP stack will obviously using a shared sequencer like Espresso, like other also able to do this.
That's a great question. It depends like what is like being shared sequenced between. But I will claim later in the talk that this is the bare basic primitive for a shared sequencer, at least within the OP stack. So is it okay if I get back to this question? Okay, cool. Okay, so some fun things about this. There's no replay protection, right? You can basically reference a remote event as many times as you want and just like pull it in, right? And so because of that, we have a higher level abstraction on top of this, which is our messenger, right? And this messenger gives two unique properties. It gives you replay protection, and it gives you domain binding, right? So like this allows you to say, I want to send a particular cross-chain message to a particular chain, right? So there's a lot of Solidity code in there. What I think is fun about this is now we finally have a use case for the anonymous event. The anonymous event no one's known why that existed for the longest time. It's like the log zero opcode. But what's fun, right, is what you can do is you can basically encode your call to a cross-chain contract, and then you just emit it from an event, right? So you encode your call, just like how you would in like Solidity, the exact same syntax works. You emit it from an event, and then you can like pull that call into another chain and then just like pass it right into a smart contract. So now you've got cross-chain calls, right? So we're like layering levels of abstraction. So now we got cross-chain calls with replay protection and domain binding, right? So what this means, now that we have cross-chain calls, we have like block building, right? So the scalability of this kind of scheme is based on the ability for block builders to coordinate, right? Because you're just like basically making these like transactions that have identifiers that like point to logs, right? If you have two block builders that are basically building on two chains, then they can coordinate to like basically, point to each other's logs that they emit like at the same time. They could like build the block together, right? So like this gives you like the primitives for shared sequencing. And I also want to claim that it gives you atomic composability. And like, people like to argue about like, what is atomic composability, right? Like, I think that you get atomic composability under the assumption of block builders that coordinate, right? And the idea is that block builders, right, it's a competitive marketplace. What's really nice about this scheme, right? So this is one of my favorite quotes right here. If you ever have a problem that's too difficult to solve, make it profitable for the MEV people to solve for you, right? Because the MEV people are competing with each other, right? So if this is a very difficult problem, right? This is like some crazy knapsack, like align like, transactions between multiple chains, right? So, the MEV people are trying to make money, so like make them compete for you to like improve your protocol, right? So that's basically what this scheme is going for, right? So just to like repeat this, right? You have like these like cross-chain messages, right? So basically, the block builders, what the block builders would do is they would include like an initiating message, and they include in the other domain they'd include an executing message that references that initiating message. But then that executing message would like emit an event, right? And then that would count as the initiating message. And then on the other side, you'd be able to include an executing message that references this initiating message. So you'd be able to go back and forth like this, right? And basically the question is like, you know, can block builders do this? Right? So this is what I was saying. How difficult will it be for the block builders to coordinate on this, right? So I do think it'll be possible. I don't know like how deep they'll be able to go with how many callbacks, but I do think that they'll be able to do at least one, you know, but they'll compete with each other, and through that competition, they'll be able to like provide better services for users. So that's what's great about this. Also, fun idea, right? Can you build like an RFQ system by basically, you know, proposing the executing side? Well, no one has created the initiating side yet, right? You can basically kind of create this like, you know, order filling kind of thing where, you know, you just like make your executing message available, and then somebody that like wants to fulfill the executing message can just like submit the initiating message. I think that this is like a really interesting design space. Okay, so some more research questions. So we have this only EOA constraint, right? If we go back to the smart contract, I'll show you. Right, this is probably like, you know, smart contract wallet people probably will hate me, but you know, we have this require message sender equals TX origin. What this means, right? This means this enforces that it's the top level call frame, right? So unfortunately, you can't use a smart contract wallet with this, but the reason why is specifically for denial of service protection, right? So the block builder can look at this transaction that's calling this function and statically analyze the call data. It can just deserialize the call data and basically look at this identifier, and then basically, it can basically look at this identifier and then basically check to see that this exists. Right, this is the log, the serialized log, right? So since it's all statically analyzable, we give like a nice easy problem for block builders. It's like just have like an RPC that points at like a remote domain. You know, you can do eth get logs at this block number, and then filter by, you know, this address. This is the address that emitted it, right? So like that's one RPC request. And then what you do is then you iterate through the logs and you see, you know, does the log index match, right? So now you have the exact log, you just use the RPC, right? And then you just serialize the log, you know, using this algorithm, very simple. And then you just compare that what you fetched from the remote RPC matches, you know, what was passed in there, right? So it's a very easy problem for block builders. And sure, it's not super scalable. You're using RPC. You know, block builders will probably do some crazy optimization where like they figure out a way to not go over the network and stuff. But, you know, naive block builder, you know, was able to just describe the algorithm and how you like ensure that this works. So the idea with the only EOA constraint, that removes the ability to do this static analysis. So it makes the problem much more difficult for block builders. What we would have to do instead is basically, you know, we'd have to emit an event here that includes the message and the identifier. And then basically the block builder, when building the block, they'd have to like pull out all of these events and then do the checking then. So it's like checking after the fact or before the fact. When you can statically analyze, you check before the fact. And if you have to like look at the event, you already did the simulation, somebody can dial a service you, so. Okay, cool. So another question is like, what is like the topology of all the chains that are like interoperable like this? Like, will it be like, a hub and spoke model? Will it kind of be like distributed or decentralized? Another thing that's interesting is like this timestamp rule, right? It allows for like intra-block time travel. So what does that mean? We go back here, right? See this identifier, right? This identifier is like a unique pointer to the log in a remote chain, right? So right here, you can see that the timestamp, so this is the timestamp that the log was emitted at, right? It has to be less than or equal to the block.timestamp, right? So all the chains are like advancing at the same timestamp, right? As they produce new blocks, they're all at the same timestamp. So basically, it's impossible to introspect on like the total ordering of transactions within a block, right? To this, right here, all the transactions kind of like, the first transaction in the block and the last transaction in the block look the same. So there's like this weird property of time travel within a block under this scheme. I'm not really sure if it's useful or not, but it's just like an interesting observation. Okay, cool. So the past. This is the past, right? Web 2, right? Web 2 architecture operates on a set of horizontally scalable VMs, right? And we have the ability to like scale up the number of VMs with demand, right? This is how we're able to like service the entire world with our services, right? So the current, right? So Web3 architecture operates on a single VM, right? Basically, what happens is, all the applications, they're all competing for this like global lock. They're the only one that's able to like do anything at a single time, right? So they get this lock, they're the transaction that's executing, and they're the only one that's allowed to read and write at that time. So the future, Web3 architecture operates on sets of horizontally scalable VMs, right? The number of VMs can scale with demand. We basically need to look to how Web 2 builds their applications and build our applications in the same way, right? And what this means is we need to like fundamentally rethink how we go about designing smart contract systems. Right now, we design smart contract systems in a way where we assume that the entire system is deployed to a single blockchain, right? And that all of the state is kind of like right there, right? That's kind of like saying that, Web 2 companies should deploy their entire, back end to a single computer. It just does not make sense. It's like impossible to scale that way, right? So we need to rethink about how to build things in an interop native way, right? And the claim is that if you can horizontally scale, you can smooth your fee market across many chains. So what this means is like you can bring your own gas to the network, right? In kind of like the equilibrium state of being able to bring your own gas to the network, what that means is that in theory, the transaction fees should find an equilibrium around the cost of the hardware, right? So what this means is that like basically if you're able to look at your smart contract system and find the like bottlenecks, right, the hottest parts of your code that's called, and you're able to basically rewrite the smart contracts in a horizontally scalable way, then you can get these sorts of benefits where when demand goes up, then you can increase the supply, right? Because right now we live in a world of gas scarcity, right? Gas is a scarce resource because like blockchains, produce it, right? And you like buy gas from blockchains, right? But like, I think that's kind of dumb. Like we should be able to bring our own gas to the network by turning on more machines. And that's like the point of this, right? Like basically, you design your smart contracts in a way where, your smart contracts don't all need to be on the same chain. And basically you have like, can think of it like templates, right? And when there's high demand, you automatically spin up a new chain that has this like templated contract in it, and then you start routing user transactions to that chain, right? And like not all smart contracts will be able to be kind of like, horizontally scalable in this way. But if you can like take your like really expensive business logic and build it into smart contracts that horizontally scale, then you can, get all the benefits of this. Right, okay, so something that I've been trying to think about, is like, what's the right abstraction to make this really easy for developers, right? So there's this idea of a distributed hash table, right? So like a distributed hash table basically lets you kind of, it's like a hash table, right? Like a key value pair kind of thing. But with a distributed hash table, it like all the values are spread out across many nodes, right? So the idea is that what if we had a library that implemented a distributed hash table but feels like regular EVM storage, right? So like if you've written a smart contract, you're probably familiar with like writing to storage, like either use like a mapping and you just like write like a key value pair into the storage, or like you do like a low level S store or something like that, right? So the idea is that we need to build abstractions that allow developers to take advantage of this like horizontally scalable idea where like they don't need to like think about it, but they just get the feature for free, right? So can we build a library that implements a distributed hash table but just feels like regular storage? And the idea is that you just have like a little off-chain bot that would like rebalance the keys across all of your nodes, right? And then the idea is that you can add or remove nodes automatically, and the whole system would self-heal. And the idea is that you'd be able to build parts of your smart contracts on top of this abstraction, and it would just give you horizontal scalability in your application. And like I said before, not all smart contracts can be built in this way. So you could imagine like some parts of your code base, your Solidity code base, could be like horizontally scalable. And then what you could do is you can kind of have this pattern where like you settle down all the state to another chain, right? And then in that chain you can that can be like your coordinator kind of like chain, something like that, right? So on-chain order books are too expensive right now. So my claim is that you can build an on-chain order book using this architecture. Because like you have to like insert orders, and then you have to like fill orders, right? That like uses like a lot of gas, right? So if you could like horizontally scale and like shard kind of your order book deterministically across like many different chains, then it should be possible to build an on-chain order book. Because like if you look at like BitMEX or whatever, like they definitely run their order book on multiple VMs. It's not just like a single VM that runs all of BitMEX or like or like Coinbase. So we need to learn from Web 2 with architecture to like be able to like take Web 3 to the next level. Phoenix. Another Ethers Phoenix, more Ethers Phoenix, and our specs. So if you have any questions, check out our specs. We have all of this specified. It's online. It's free for anyone to use. We're starting to work on it now. Yeah, that's my talk. Okay, who's got questions?
Great way to involve map players, but like would they also be centralized problems maybe?
Well, there also be what?
Centralization problems maybe?
That's a great question. Okay, so centralization problem. So every time that you have like an interoperable chain, right, it adds an execution requirement or a trust requirement for that chain, right? Like the sequencer needs to basically, when the sequencer is doing this verification of the cross-chain messages, right, it needs to either trust like a remote entity that did the execution, or it needs to do the execution itself. So it makes being a sequencer more expensive. Also the same thing for like a full node. It makes it more expensive to be a full node because if you're syncing as like a full node, then you need to like do the same sort of checks the sequencer does to like make sure that the blocks are valid. Because if you're a full node, you want to like, reorg out invalid blocks the sequencer produces because it's like a checks and balances on the sequencer. So the more chains that become interoperable, it does increase the hardware requirements, which is a centralization vector. We have been thinking about how to fix this. I think that when vertical trees are accepted into L1, when L1, it probably won't be the next hard fork, but the hard fork after that, they will, so it'll probably be like 2+ years from today, they will implement vertical trees. And what vertical trees gives you is stateless execution, right? So the idea of stateless execution, right, like you don't need the full database to be able to like verify the block. You can be given a witness that basically includes all of the state that the block touches during its execution. So without the proof being too large, right? If we did that now, the proof would just be too large. You wouldn't be able to send it over the P2P network. So one way to like decrease the kind of centralization vectors that are introduced with this would be to use like a stateless execution scheme where like the blocks are gossiped around the P2P network and then nodes themselves can just like, statelessly execute the blocks of other chains, right? And it makes it a lot easier to not need to trust like the remote RPC or like not need to like run the full node of a remote chain. And I think that Near has a design. I know that they've moved to stateless execution for like their sharded execution. So this is like kind of similar to that, but I don't know enough about their design to like talk about it in depth.
Following that, not sure if you see my last 2 slides from my talk. How do you think about async composability compared with like atomic composability? Do you think, I guess it's more like from the application point of view, do you think there are like, how many use cases do you think that requires atomic composability? Or you maybe in most cases like async composability is fine, which means we can able to settle execution proofs on multiple chains. At least at the snapshot of time what's happening, and then you actually can, to some extent, avoid the centralization problems.
Yeah, I think that's a great question. So I think for like DeFi use cases, atomic composability for like getting ARBs, that's definitely like a big use case there. I also think that there's like the definitions of atomic and async are very weak definitions, and they like I bet you that we have different definitions. So like there's some notion of like force inclusion transactions here, I think. Like some people might believe that atomic composability implies some amount of like force inclusion. That might be like one case. Under this case, like I'm claiming that you can do atomic composability without force inclusion. I think that from a UX perspective, the like speed is just like a magical moment, right? Like we want to like create these like user experiences that are just like, the user like absolutely falls in love with and like they won't use anything else, right? So that's like a benefit that I see of like the atomic scheme. right? But like everything has trade-offs, right? So like one thing I've been thinking about is like how do you use, ZK proofs like in a scheme like this, right? And I think that like the basically the proof generation time is just going to be like too high to like allow for any sort of like within block kind of thing.
We can talk about that.
Okay.
I guess the higher level idea here seems to be, I feel like, I think in the 1 to 2 years, latency will be greatly reduced by both hardware and the neural proof systems, right? So that part I'm pretty confident. But I think it seems that there are some like open questions about the UX and especially specific use cases like you mentioned, like DeFi and a few others. From my point of view, I don't think the speed is an inherent limitation of the ZK side. Is quite temporal because there are many like newer research and like newer hardware acceleration coming. But I do think the UX part seems to be quite interesting to see how you're going to play.
Yeah, like, and I think it really comes down to like the block builders, because the block builders under this scheme, the block builders are the ones that are responsible for like, building the two blocks like in tandem that include the pointers to each other, right? So basically without the block builders, this scheme is like not that good, right? Like this scheme is completely based on block builders competing with each other to provide, more cross-chain messages in the same blocks.
I have one question, but you mentioned that you're very interested in MEV providers kind of solving this issue for you. Like, have you thought all about like interplays with like a system like Flashbot Suave or just like the normal MEV boost like pipeline?
Yeah, totally. So I've definitely talked to Flashbots about this. Basically, it's just like a game of like, bidding on log indices. We spent some time trying to figure out if we could like make the API for block builders better, but then decided it was a rabbit hole because basically like you need like to be able to uniquely identify an event, and like maybe like a different way to do it is like, do like transaction index and then like relative offset like within that like transaction. I don't know, there's like different ways to like uniquely identify the event, but like at the end of the day you need to like have these unique identifiers that like correspond to each other. So I think that it could be possible to use Suave to do something like this. I've heard a million different definitions of what Suave is, but I do know that like Suave is supposed to allow you to program MEV boost auctions because like, right, MEV boost gives you like this auction where you can basically like bid on like the proposer, including your block, right? So, but it's like native code, right? You have to have DevOps people, like you have to cut a new release of the code. You have to update the code, cut a new release, have your DevOps people like, update it. And you need to do this every time you want to change the auction, right? So with Suave, it's supposed to like let you define your auction in the Solidity. Is that your understanding?
Yeah, like you, I don't really know I do not know what Suave is.
Okay, totally. I think it's supposed to just let you define like an MEV boost auction in Solidity. That's like the example app. And then you can like define like other types of auctions. And then it saves you from needing to like, have DevOps people update the code. Anyone can just deploy a smart contract that defines an auction, right? So you could build an auction for log indices. But I don't know if that's good UX or not.
Got it.
Okay, cool.